This short video is concerned with the central limit theorem, which, roughly speaking, states that a sum of a large number of independent and identically distributed random variables is approximately normally distributed. Now that statement is imprecise, so let's clear it up. Let f be a distribution with mean, mu, and variance sigma squared. And suppose that x1, x2, x3, etc. are independent and identically distributed, all with the same distribution f. Let x bar n be the sample mean of the first n many of the x's. Then the central limit theorem states the following. For large n, the quantity Zn, defined to be the sample mean minus mu divided by sigma over root n, will be approximately standard normal. Now just recall that the sample mean is an unbiased estimator of the true mean, in other words, that the mean of the sample mean is mu. We also showed earlier that the variance of the sample mean is sigma squared over n. And so here we are simply subtracting the mean from x bar and dividing through by its standard deviation. In other words, Zn is just the standardized version of x bar. So we already know that Zn has mean 0 and variance 1. The interesting point here is that Zn is also normally distributed. We provide here an outline of the proof which uses moment generating functions. Suppose first that the xk all have mean 0 and variance sigma squared. And let us consider here the moment generating function of the sample mean. We've dropped the subscript n in order to simplify notation. The moment generating function of x bar evaluated at t by definition is given by the following expectation. Now, since the random variables xk are all independent, this exponential and this expectation split as follows. And each of these factors is just the moment generating function of xk evaluated at the point t over n. Since all the xk's have the same distribution, they also have the same moment generating function, and therefore when we take a product with n factors, we get the nth power of the moment generating function of a random variable x with distribution f evaluated at t over n. Now define ft to be the logarithm of the moment generating function of that random variable with distribution f. This x here is not the sample mean, it is a random variable with distribution f. Let's Taylor expand this up to order 2 about t is equal to 0. In that case, the logarithm of the moment generating function evaluated at t is just f of 0 plus f prime 0 times t plus a half f double prime 0 t squared plus terms of order t cubed and higher. Now f of 0 is just the logarithm of the moment generating function evaluated at 0, and the moment generating function of any random variable evaluated at 0 is 1. So this is the logarithm of 1, and the logarithm of 1 is 0. This term disappears. Next, when we look at the derivative of the logarithm of the moment generating function, we obtain the following term. Now the numerator is just the first moment of the random variable x, in other words its mean, but we're assuming that x has mean 0. So this term disappears as well. If we look at the second derivative of f evaluated at 0, then we get the second moment evaluated at 0, and since the mean is 0, this is just the variance, in other words this is sigma squared. A little thought will now show that the logarithm of the moment generating function evaluated at t is a half sigma squared t squared plus terms of order 3 and higher. Now using the relationship between the moment generating function of the sample mean and the moment generating function of x on the previous slide, we obtain the following. i.e. it's approximately equal to a half sigma squared n t squared. That's the logarithm, so the moment generating function of the sample mean is approximately equal to e to the half sigma squared over n t squared. Note that the second order Taylor expansion for the moment generating function of x evaluated at t over n is only accurate when t over n is small, i.e. when n is large. So the approximation for the moment generating function of the sample mean gets more and more accurate as the sample size n gets larger and larger. Now we recognize this to be the moment generating function of a random variable which is normally distributed with mean 0 and variance sigma squared over n. Since the moment generating function of a random variable completely determines its distribution, we see that x bar n must be approximately normally distributed with mean 0 and variance sigma squared over n. If the xk are assumed to have mean mu and variance sigma squared, then applying the above argument to xk minus mu shows that x bar n minus mu is approximately normally distributed with mean 0 and variance sigma squared over n. And hence, if we divide through by its standard deviation, the resultant will be approximately standard normal. Just an example to show how the central limit theorem works. We start with small numbers first. Here we have 5 samples, each consisting of 10 draws from the Poisson distribution with the rate parameter lambda is equal to 2. So the first column is the first sample of 10 draws, the second column is the second sample of 10 draws, etc. If I take the mean of each of these samples, I obtain 5 means. So the first element here is the mean of the first column, the second element here is the mean of the second column, etc. So what I have here is 5 draws from the distribution of the sample mean with n is equal to 10 sample points. Now we normalize x bar, in other words we subtract its mean and we divide through by its standard deviation. We know that the mean and the variance of the Poisson lambda distribution are both equal to lambda. And then we can plot a histogram. Now this does not look remotely normal because we took only 5 samples and the sample size was very small. What we're going to do now is take a large number of samples, say 1000, of a large number of draws, say 200. We can compute the means. We will now have 1000 means, so 1000 draws. We can normalize these. And if we then plot the standard normal PDF, we see that we sort of have a match. So when we take a sample of 200 Poisson random variables and we take the sample mean, that is approximately normally distributed, as shown by this histogram.